So this video is an introduction to electrophilic aromatic substitution. So aromatic compounds, like benzene, react differently than alkenes do. So remember with alkenes, say I have cyclohexene here. If I react that with bromine, I'll get addition across the double bond. So it'll give me anti-addition, and then I'll get my enantiomer. If I do the same reaction, but this time with benzene, I get no reaction. The stability of the benzene ring, the conjugation of it, all that electron delocalization, that's making it more stable, so less reactive. Under the right conditions, using the right reactants though, you can get aromatic compounds to react. But the reaction is a substitution reaction, not an addition reaction. And that's why we call it electrophilic aromatic substitution. So there's a few different electrophilic aromatic substitutions that will happen depending on what reagent you're using. So the first one is halogenation. If I react benzene with bromine and iron, I will get my product of the electrophilic aromatic substitution, which is a mono-substituted product. So I don't get two bromines added here, and I still keep my double bond. I'm substituting a hydrogen for a bromine. So here's how the reaction works. The first thing I do is I react bromine with the Lewis acid iron tribromide. So in this reaction, my bromine reacts with the iron and I get a complex. Positive formal charge on the one bromide and then a negative formal charge on the iron. It's this complex that reacts with the benzene. So now I have my benzene. And I react this with the complex. The pi bond from the benzene attacks the bromide, electrons move over to the other bromide. So now I'm left with this. Right, there's resonance going on here, so I can move the double bonds around. Right, this is known as a sigma complex when you have your resonance within that bromide, within the benzene ring. Right, so my carbocation will move over to here now with the resonance, and my bromide from the iron tribromide complex can attack this hydrogen, and the electrons from that hydrogen move down to reform the aromaticity in the ring. And now I'm left with my final product of the electrophilic aromatic substitution, in this case, halogenation. And of course, I have my catalyst reformed. So the iron tribromide here, that Lewis acid, is a catalyst. I can do the same process with chlorine as well. The mechanism's identical. The only difference now is I have to use a different Lewis acid. So if I react it with Cl2, this time I'm going to use aluminum trichloride. But I'll get the same type of product I had with the bromide. Instead, it's a chloride that's substituted on. So that's halogenation with electrophilic aromatic substitution. So next up is going to be sulfonation. In this reaction, I have benzene, react it with fuming sulfuric acid, and I get my product of that. So sulfonation, right, because I'm adding this sulfur compound onto the benzene ring. So fuming sulfuric acid produces SO3 gas. And SO3 gas is a very strong electrophile, so it works well for electrophilic aromatic substitution. So for the mechanism now. I react this with SO3. Right, again, great electrophile. The pi bond comes and attacks. Leaving me with carbocation there, and then sulfur compound over here. Water now comes in, because I also have a hydrogen here, right? So water comes in and deprotonates and reforms the double bond. And again, it's water doing this in this case, acting as the base, because I'm in strongly acidic conditions. So I can't have hydroxide in solution. So water is going to be what's acting as the base. Minus, then last step, I now need to protonate that O minus, so I have H3O plus in solution. So I'll protonate and get my final product of the sulfonation. Now this reaction is dependent on the concentration and then the temperature of the H2SO4 you're using. I can reverse this and go from my sulfur substituted benzene back to regular benzene if I use dilute H2SO4. So just something to take note of, you can change the reaction conditions to go from your product back to your reactant. The last class of the electrophilic aromatic substitutions I'll discuss in this video is nitration. And like it sounds, I'm adding a nitrate group onto or a nitro group onto the benzene ring. So the first step of this is interesting. It's an acid-base reaction between two strong acids. Right? It seems weird, but acidity is all relative. And the two acids I'm using here are nitric acid and sulfuric acid. Sulfuric acid is stronger than nitric acid is. So if you put them together into solution, you're actually going to have an acid-base reaction where the nitric acid acts as a base. So this is the structure of the nitric acid. I react this with H2SO4. And this will give me now a protonated nitric acid. So now I have two positive formal charges next to each other, which obviously isn't going to be very stable. So the electrons from the negatively charged oxygen will move over to form a double bond, and it'll kick off the water, because water is obviously an excellent leaving group, and this will leave you with a wonderful electrophile. Right, that's a great electrophile. Nitrogen with a positive charge. Benzene will attack that very quickly. So now my benzene ring will come and attack this great electrophile, leaving me now with a carbocation, and then my nitro group that I've added onto the ring. Water comes in, given these are acidic conditions, and deprotonates, reforming our aromaticity, and I have my final product installed, the nitro group. What's great about this reaction too is now I can take my benzene ring where I've added on the nitro group and easily, using either iron or zinc along with HCl, I can convert this nitro group into an amine. And amines have a variety of functions in medicine and in other reactions. So to be able to install the nitro group onto the benzene ring readily using this reaction, and then being able to convert that to an amine, is very important for applications in synthesis of organic compounds. Alright, so my next videos are going to be on Friedel-Crafts alkylation and acylation, which is another class of electrophilic aromatic substitution. And then I'll discuss some on, if you have substituents on the ring, where are your new substituents going to be added? So those will be discussed in the upcoming videos.